All right, we're going to finish this up by going back to one step to item J. We can look at this. We can add steps 1 and 2, and we can see that the overall reaction is 2N2O reacts to form 2N2 plus oxygen. The rate, however, is only proportional to N2O, and the reason for this is that the rate has to include the slow step, and the slow step is the first step, not the second step, or not the overall, and the first step only has one N2O molecule in it, so that's all we need to put in our rate law. Rate is K times N2O. Now let's take a look at the second, or the next one. Here I've got, rather than the rate limiting step being the first step, it's some subsequent step. So I can look at this and see, according to what we've been given, the slow step is the second step, and I can write my rate determining step here. And so rate is equal to K2 times NOBr2 times NO. Now the problem here is that NOBr2, looking at this, NOBr2 is an intermediate, and an intermediate's unstable, frequently just doesn't even have a concentration that we can measure. And so I needed to rewrite this so it's expressed in terms of the reactants that don't have any intermediates. Now, since the first step is a fast reversible process, I can say that the rate of the forward reaction is equal to the rate of the reverse reaction. So that allows me to write K1 NOBr2 is equal to K minus 1 times NOBr2. And if I solve for NOBr2, I get that that's equal to some odd thing, K1 divided by K minus 1. And really that's just some other constant, times the concentration of NO times the concentration of Br2. Now, when I plug this back into what I got in part K, I find that my rate is equal to K times NO squared times Br2. So in general, when a fast step precedes a slow step in a mechanism, you have to do a little bit of algebra, rearrange in order to get the intermediate out of the equation. You can do that by assuming that an equilibrium is established in the first step. We're going to define the term catalyst as a substance that changes the speed of a reaction but is itself not consumed. So here we've got a couple of steps. When we add these two steps together, we can see that the overall reaction is 2 moles of peroxide reacts to form 2 moles of water plus oxygen. And in this particular reaction, Br2 is an intermediate because it's created in the first step and then consumed in the second step. It is neither a reactant nor a product in the overall reaction. On the other hand, Br minus is a catalyst because it's present as a reactant in step 1, and then it is formed as a product in step 2. So there's overall no real change. You start with Br minus and you end with Br minus. Catalysts can function by stabilizing a transition state, which would lower the activation energy. That increases the rate of that step, but otherwise doesn't do anything to the reaction. Now, they also may participate in the formation of a new intermediate, which provides a new mechanism that provides a faster way to get from reactants to products. Now, when we look at this reaction diagram here, we've got two pathways. One is an uncatalyzed reaction in red, and the second is the catalyzed reaction in blue. Now, yes, there is an intermediate, and we're going to have to take that into account when we write our rate law, but we can do that based on our first step, which is assumed to be a fast equilibrium step. This has the function of lowering the overall energy, the activation energy, which speeds up the slowest step. You can see that the reactants aren't really changing, the products aren't really changing. All it does is speed things up by lowering the activation energy. Then our last part here is that a biological catalyst is known as an enzyme. This is an anatomy and physiology word for catalyst. provides a particular type of chemical to mate at a particular site on a protein to speed up the formation or some sort of reaction that the protein is involved in. All right, that concludes our notes on kinetics.